All right, welcome everyone to today's Dream CPAR seminar. It's my real pleasure to welcome back to Berkeley Wenchao Li. Wenchao is currently on the faculty at Boston University, where he holds the Peter J. Levine Professorship. He's been at BU for a few years now, 3 or 4 years.
3 years.
And before that, he was at SRI very briefly, and before that, he was here at Berkeley. For some time, for a bit longer, yeah. Because he got both his undergraduate and his graduate degrees from Berkeley. So it's always nice to welcome back an alum. Wenchao, for his PhD, worked on the topic of specification mining, but in a broad sense, and his thesis was recognized with the ACM SIGDA Dissertation Award. And then he also at BU has been doing some very interesting work that cuts across formal methods, robotics, CPS, and AI and machine learning. And today he'll be sharing with us some of his most recent work on higher assurance verified machine learning. Okay, welcome.
So thank you very much for the kind introduction. It's always good to be back at Berkeley. So today I will talk about proving safety of neural network control systems, and in the case that we don't actually get a proof, then how to improve safeties for those systems. So again, I'm Wenchao Li from Boston University. This is joint work with my PhD student Jiameng Fan, and also Chao Huang and Xi Zhu from Northwestern University, and Xin Chen from University of Dayton. So let me first tell you a little bit about neural network controllers. So spurred by some exciting developments in deep learning in recent years, there's been a growing interest in using neural networks as the central decision makers for a number of tasks. So these neural network controllers can be trained using a variety of training learning paradigms. So reinforcement learning or deep reinforcement learning is one of them, right? So in 2015, people demonstrated that the DRL agents can achieve human level performance for a set of Atari games. But of course, if the safety requirements not properly encoded in the reward function, then you might actually end up with unintended behaviors. Actually, it looks like my video is not showing. But anyway, so what you should see here is the vehicle should keep crashing, even though we achieve a reward that's 20% higher than what the human player can achieve. Another powerful learning paradigm is imitation learning, which means that you want to transfer the knowledge of an expert human to the learning agent, and people have shown some success in robotic manipulation tasks and lately in autonomous driving as well. So a common thing that you would notice here is that these neural network controllers are mostly used in simulation environments. So the natural question to ask is whether these can work actually safely in real-life scenarios. Speaking of real-life scenarios, recently there's been some work that drive the development of neural network controllers. And the setting was driven by practical constraints, such as runtimes or compute resources. And in this case here, you actually want to approximate an optimal model predictive controllers using a neural network controllers because inference is really fast on neural networks. Okay, so these are neural network controllers. Let's see how they're actually used in a typical cyber-physical system. So I've simplified the system diagram in this case where I would, for now, assume perfect actuations and sensing. So essentially, you have a controller that controls a physical plant. For verification, we assume that we know the model of the dynamical systems. For instance, it might be governed by some ordinary differential equations. And these are just some notations, so I use X to represent state and U to represent the control values. And this is a sampled data control system, which means that I would sense the state of the system at time t, right? I would compute the corresponding control value for that state, and after some delay of delta, then I would apply that control value to my physical plant. So in terms of system execution, that is how what you would see. The system is initialized in some state x0, potentially in a set of initial states. then the system would evolve to some other state, and at time delta, you would apply the control value u, and then you would hold that for the duration of delta. Okay, and then the system continue to evolve. So again, as we're just doing zero order Hoe, we are assuming that we have perfect sensing and actuations. The approach would generalize to settings where the sensing errors and actuation errors are bounded. So a neural network control system is simply a control system where a neural network, a feed-forward neural network, or maybe even RNNs, is actually used as the controller, as opposed to a traditionally designed controller. Okay, so what are the problems that we might be interested in verifying? So let me just show you one experiment that we did in our lab. So we are trying to train this robotic arm to move to some random goal states within this workspace while avoid hitting these box obstacles on the table. Okay, so you can do this either with reinforcement learning or with imitation learning, and then you get fairly good performance, and you get some assurance that this robotic arm never hits this obstacle and can reliably get to the goal state. The question is, if we were to deploy the same policy on an actual robot, would that work? So here's some simulation example that we did on the actual robot. So this case, the goal position is very close to the obstacle, and the robotic arm has to navigate around this box obstacle, right? So again, the question is, does it actually work? So what's the mathematical problem here? We are looking at reachability. So the way that this is formalized is the robot or my system is initialized in some initial set x0. I'm giving a target set xf. I'm trying to reach the target set from a state in the initial set while avoiding some given avoid set. Okay? So the specification here is called reach avoid. Again, what I want to verify is that starting from any state in the initial set, decide if the neural network control system can actually reach a state in the target set and some horizon t while avoiding the avoid set. Okay? So you might have heard of another kind of reachabilities for neural networks. And this is only concerns with the neural network itself and doesn't concern the physical plant. So the way that it works is you might be interested in computing the output reachable set R for some neural network function f. Okay, so R is represented in this way. And then you might want to check, or might be interested in checking whether the reachable set is inside some target set. And typically, doing exact reachability analysis might be difficult, so you can compute an overapproximation of this reachable set, and hopefully that overapproximation is high enough for you to verify this property. Okay, and this is also called output range analysis by some researchers. So there are many techniques that people have developed in recent years to look at this particular type of reachability question. I will show you the connection with the reachability problem of neural network control systems in the next slide. But these techniques include SMT-based analysis, which actually can be exact. But in terms of efficiencies, you might want to do interval propagations or some shape propagation across the neural networks. And people have also developed MILP formulations to answer this output range problem. Okay? So the primary use case for this type of reachability analysis is look at adversarial robustness. People have tried to apply this to do robustness certifications of neural networks. And in terms of maybe the connection to control is, people have used these to answer, to check properties of a aircraft collision avoidance systems, where the advisory control is actually given as a neural network, so a set of neural networks. Okay. Right, so we've seen in 2 slides why this is relevant. But for the questions of reachability itself of neural network control system, the first question we ask is, what's the complexities of the decision problems, or maybe whether that's decidable at all. So it's obvious that the NNCS are at least as expressive as nonlinear continuous systems. So the exact reachability problem is undecidable. So what we ended up doing, or what existing approaches would end up doing, is to compute overapproximation of the reachable set. Okay. So just to briefly mention the state of the arts. So the first approach essentially does polynomial regressions on the neural networks, and then uses a tool for reachability analysis of nonlinear hybrid systems. The second work is interesting in the sense that it leverages special properties of certain activation functions in the neural network controllers and transformed the neural network control systems into one big hybrid automata, and then leverage reachability analysis tools for hybrid systems to answer that questions. So our approach shares some similarity with the first one and also with the second one in that we used this particular reachability analysis tool for nonlinear hybrid systems or hybrid systems with nonlinear dynamics. But we can handle a more general class of neural network control system, of neural networks, which I would describe later. And we can also get tighter overapproximation of the reachable set. Okay. So just to give you some background, to answer the reach avoid or the reachability questions, we want to we'll do forward reachability, and then we'll construct these flow pipes, which are essentially a finite set of higher order Taylor models. So imagine that for this initial set that I start with, I will construct a flow pipe that is visualized in this fashion, right? And then I will keep doing that, and hopefully my flow pipe will never hit the avoid set, right? And then my reachable set at time t would be contained in the target set. So I have a positive answer to the reachability problem. Okay, so there are some existing tools of actually doing this, which is FlowStar is an example. Okay, so going back to the question that we have a lot of nice techniques to analyze reachability for neural networks, not for neural network control systems. Can we directly apply those techniques to answer the reachability questions for neural network control systems? Okay, so think about this simple algorithm that I would use output range analysis to come up with an interval over approximations of the output of the neural networks. I would just feed that interval into this tool that does reachability analysis for dynamical systems, and then I repeat. Okay. So here's a simple example where the dynamics of the system is given by these differential equations. Let's say we have a very simple neural networks with actually hybrid activation functions that act as the controller. And this is what we observe. Okay. So the red trajectories represent simulation trajectories from a specific initial state. So the initial set is somewhere here at the top right. The green rectangles represent the reachable set that you compute at successive time steps. And what you can observe is that this reachable set computation blows up fairly quickly. Okay, it starts being able to track the simulation trajectories quite well, but then it blows up. So what's the problem here? The problem is that if you were just doing output range analysis on doing interval over approximation, then you would fail to capture this input-output mapping that the neural network controller has. Okay, so essentially you don't know the mapping for a specific state to another. So we cannot do this approach. So the way that we are able to address this issue is let's consider some simpler function approximation of the neural network, so then I don't have to deal with the variables in the neural network. So I don't have to deal with the neurons and the weights. So in our approach, we use this specific type of polynomials called Bernstein polynomials to approximate the neural network controller. And the advantage of actually doing this, using this type of polynomial is that the approach works for any Lipschitz continuous neural networks. And indeed, many neural networks, and the neural networks that you would typically see, they are all Lipschitz continuous. Okay? So these can handle ReLU activation function, but tangent activation function as well, or the combination of these. Okay? So suppose in these particular diagrams, the red curve represents the actual neural network function. Then we would do a regression with Bernstein polynomial to get an approximation of that function. And now to be able to get a sound over approximation of the reachable states, then we have to do some error bounding. Right? So in this case here, you want to be able to say that the error is within some epsilon. Okay? So the challenge is how to manage this particular error. So it turns out that there's a formula that gives you the error directly, okay, which is shown here. Okay, so suppose this BFD is a Bernstein polynomial with degree d, and the difference between that functions and the neural network function f, you can obtain a bound. Based on the Lipschitz constant or a Lipschitz constant of the neural network. So typically you would come up with an upper bound for the Lipschitz constant. The problem with this is this particular theoretical bound, while it's nice as an analytical form, is often very pessimistic. So M is the number of inputs, right? B is the degree of the Bernstein polynomial. And by looking at this, you can see that the error can be quite big. Right, so if the Lipschitz constant is big, or if the degree of polynomial is big, and so on, it is small, and so on. Okay, so the challenge is how do we make this error analysis tighter? So what we came up with is an adaptive sampling scheme, and the idea is quite simple. Okay, so first we observe that the Bernstein polynomial approximations is also Lipschitz continuous with the same Lipschitz constant. This is a known result. And this allows us to do partitioning. Okay? So I can partition now partition my state space and then analyze each partitions individually. So the details don't quite matter, but essentially it's just a triangle inequality. And I'm looking at this particular partition when the C is the center of that partition. So I would sample that center point, and then I would be able to construct a smaller, essentially the error bound for that particular, for the approximation in that partition. The nice thing about this is the finer the partition you use, the approximation error. So in the ideal case, you would get to the actual approximation error. So the over-approximation error would approach zero as you increase the partition. And we can also do this adaptively. Because the max error, the error would now be the max error across all partitions. So if you have a large error in some of the partitions, you can adaptively partition. So you can further partition the space to control the error analysis. Okay. So just to give you an idea of how this works, this is for the same systems with the same neural networks and same dynamics. So with our approach, we are able to actually give a positive answer to the Reachability property. And again, the green pipes represent the flow pipes construction for this particular system.
So yeah. The Bernstein polynomial approximation is being used already for nonlinear dynamical systems, right? By Tommaso in his thesis work.
Yeah. So
can you explain what the similarities and differences?
Yeah. So this is actually doing a Bernstein polynomial approximation of the neural networks.
Right. So it's just applying it to different class of functions.
Yeah.
Are the actual techniques similar, or?
So I mean, Bernstein polynomial has been around. So there's no innovation in terms of how to do the regression. The innovation is how to do the error analysis, and so that you have a tie-over approximation. Yeah, for Lipschitz continuous functions. Right, and most neural networks, I mean, that's the ones that I've seen, they're all Lipschitz continuous. The question is, I mean, computing the Lipschitz constant of the neural network itself is a research question. So it's fairly easy to get a upper bound, right? But that upper bound might also be very pessimistic. Yeah. Yeah. So we also compare with others' existing approach. So Verisig is the approach that converts the neural network control systems into an equivalent hybrid automaton. Sherlock is an approach that handles ReLU networks based on the MILP formulation. So first thing to notice is that our approach can handle neural networks with hybrid activation functions. So the ones, for example, with ReLU and tanh, whereas the other approach cannot. And if you look at these, basically A, B, C, and E, we are essentially comparing with Verisig, and the gray rectangles represent the Flowpipe constructions with the Verisig approach, and the greens represent the flow pipes that we get with ReachNN. So you can see the overapproximation is a lot tighter, right? So in this case, neither approach can give a answer to the reachability question.
Sherlock so actually unsound
there? There's no answer. So Sherlock just cannot handle tangent sigmoid because you realize. Oh, sorry. So this blue rectangle is actually represent the target set. Yeah, this is the target set. Yeah, so Sherlock is these deep blue lines. So Sherlock only works for example D because it can only handle ReLU networks. So, but you can see that Sherlock is actually does a fairly good job in terms of bounding the overapproximation. And also because the type of analysis that they do. So they actually leverage the fact that it's a ReLU to construct the MILP. But comparing with Verisig, our overapproximation of the reachable set is typically a lot tighter. For ReLU networks, we are not as tight as Sherlock, but we can handle more general neural networks, especially those with hybrid activation functions. So again, this is showing, the red lines show the trajectories. We're starting from initial state top here at the top right, and then the target set is indicated by this blue rectangle. So we did this work, and then we were able to verify relatively simple neural network control systems. And we are hoping to see if we can push this technology further. So one observation that we made was that if you're looking at the same dynamical system, but with slightly different controllers, and the difference is actually in the Lipschitz constant of those neural networks, and we observed that if the Lipschitz constant is large, then our tool takes a long time to run because of the partitioning that it has to do, and also to control the error. And also, still, the reachable set would blow up fairly quickly. But if we are able to reduce the Lipschitz constant of the neural network, and it can do push the reachability analysis further, and also reduce the runtime. And in this case, if you reduce the Lipschitz constant of the neural network to about 9, then we actually can verify the system, right? So this reachable set is fully contained in the target set.
What's the dimensionality of these systems?
In this example, it's fairly small. I don't remember, so 4 or something like this. I will talk about the challenge with high dimensional systems. So we also observed the same thing, even when applying a different tool, which is Verisig. So again, if the Lipschitz constant of the neural network is smaller, it's fairly natural to actually to explain why we would have this observation, right? Then we can push the reachability analysis further so that the reachable set doesn't blow up as quickly. So now, based on these observations, we asked the question, would it be possible to co-design the neural network controller for actually safety verification? So instead of verifying a controller that somebody gives us, could we sort of building this knowledge that I want to reduce the Lipschitz constant as we train the system? But at the same time, we do not want to restrict the way that the neural network might be trained, because it might be trained using RL or with other type of technologies. So we leverage the idea of this knowledge distillation to transfer the knowledge of a trained neural network into something that is easier to verify. So the basic architecture of knowledge distillation is that you have a teacher-student model, and then so the teacher being the trained neural network and the student model being the easier to verify neural network. And the way that you can do this regression is by querying the teacher for input and output pairs. So fairly simple paradigm. The interesting thing now is we have two objectives, right? One is reducing the loss, which is the difference between the new neural network and the original neural network, but also maybe reducing the Lipschitz constant out. Suppose I have some target Lipschitz constant, whether 100 or 10. Okay. So you might consider a weighted sum of a combined objective, right? But how do you decide the weights? So we ended up doing a two-objective gradient descent. So you have a gradient for each of these objectives. And in the case where the gradients kind of actually agree, meaning that if you pursued along those gradients, you would be reducing both of the loss functions. Then you can go in the direction that's the angular bisector of glib and gloss. If they don't agree, then we first prioritize in reducing the loss because you want the neural network to at least perform in a similar way as the original neural network. So you would project gloss into a plane that is perpendicular to glib, so that if you pursue this particular gradient, then you would not reduce glib. And if you can get the loss to an acceptable threshold, then we have a reprioritization scheme that reprioritize on pursuing the direction closer to glib. Okay. So it's a fairly simple idea. But let me show you what that allows us to do. Okay. So we look at an autonomous driving setting. It's fairly simple. These are the yellow lines represent the walls. This is a small obstacle here. This is my target set. So again, the red lines represent simulation trajectories of these neural network control systems. And again, the green pipes represent the flow pipes. So if we don't do anything, right? So we just train these neural networks actually from an optimal controllers in this space. The reachability analysis was not able to show that was not able to verify this reach avoid property because this reachable set over intersects with these particular with the wall. Okay, so the answer is unknown. If we set the L target to 100, we get a different neural network controller. But this time we're able to push the verification further. But unfortunately, the answer is again unknown because the reachable set intersects with the wall or the obstacle, the avoid set. So, and this is the, so if we set the L target to be 10, and sometimes it just stops here because we have a parameter for the regression error, then I get a different neural network controller. You can actually observe that this neural network controller steers more slowly than the other ones because it has a smaller Lipschitz constant. But for this particular control task, it also satisfies the specification, at least in simulation. And we are also able to get a proof that no matter what initial state it starts in a small this initial set, it can safely avoid the obstacles and reach the avoid set. Okay. All right, so this is what we did. So what are the challenges? So I've shown you sort of, relatively small examples with a car navigating in 2D. One thing to know that is all these existing approaches, including ours, do not scale to large number of inputs. Unfortunately, this is one big challenge that verification faces.
What's the largest?
Maybe 6. Yeah, I don't remember the exact numbers. You mean it depends on the problem as well. The nice thing is the neural networks can be quite deep. So the depth does not matter so much as opposed to the dimension of the system. I mean, for some certain systems, you can look at maybe 10 or something like this, but typically not more than that. Right. So I'll talk about maybe some thoughts on how we can overcome this challenge at the end of the presentation. But the other thing that we notice is that verification requires knowing the dynamical model. Okay, so it's always verifying with respect to some model that I believe in. But so and the proof relies on this knowledge. But the claim I want to make here is that improving the safety, maybe for model-free learning, may not require knowing the dynamical model. Okay, and this is inspired by the fact that there's a lot of advances in machine learning, and in particular in maybe reinforcement learning, where they can handle model-free environments. Okay, so this is goes to the second part of my talk. And the problem that we are looking at is safe exploration in model-free RL. So we are going from getting a proof of safety for the reachability specification for system where we have a good model of, to a setting where we are interested in improving the safety of the learning agent during explorations in a model-free learning setting. Okay. So first, let's look at a fairly well-known approach for doing safe exploration. This is actually developed here at Berkeley, and the technique is called constraint policy optimization. So the formalism is built on top of constraint MDP. So essentially, you have Markov decision processes augmented with some auxiliary cost function C. Okay, and you want to restrict policy to those where these constraint returns, right? Essentially, a cumulative return on the cost function should be less than some threshold D. Okay, so the RL problem is, again, to find an optimal policy subject to these constraints. So the first thing that we notice is this is a trajectory-based notion of safety. So we are not looking at state-based safety because we're looking at the cumulative cost returns. And we check whether that's smaller or equal to some threshold. Okay. The second thing that we notice is that what if I have a model-free RL setting, right? So here we need to know the cost functions, which arguably is as hard as knowing the model. So if I don't know the model, how would I get these cost functions, right? So the question here is hard to design these cost functions, and also it's hard to know this threshold D. So this constraint policy optimization approach relies on knowing C and D. Okay, which are both difficult to obtain in a model-free setting. So we can resort to some statistical tools, and we are inspired by the line of work of using Gaussian process estimations to produce a statistical safety certificate. Okay, so the way that it works here is that you can use Gaussian process to approximate the unknown dynamical model. Okay, and then as you explore, you get new samples that improve your Gaussian process estimation, right? But you would only explore it in the regions that you have a good estimate of. Okay, and then you slowly grow your safe set until you cannot explore it further. Of course, there are issues with this type of approach where maybe your safety regions actually are disconnected, and it has problem with actually exploring those regions. Okay. Our ideas, which is different, while we're inspired by this line of work, but it's different in the sense that instead of using Gaussian process to approximate the whole dynamics, imagine this could be a high-dimensional system. We actually use GP to only approximate the part that's relevant for safety. So what it means is we will approximate a real-value function that captures only the evolution of trajectory-based safety. Okay, so this would be some cost function or some auxiliary cost function that I have designed, but it doesn't have to be very exact. And on top of that, we leverage ideas of control theory And in particular, we would construct a function approximator that actually act as the control Lyapunov functions. And what that actually gives us is essentially similar to asymptotic stabilities, what you want to use CLF for, is an ability to recover from unsafe states. And what that means is asymptotically you would converge to safe behaviors. Okay? So now the picture will look like this. If you do use a favorite deep reinforcement learning algorithm with these function approximators for your policy and also for Q, right? Like DTPG is an example. Now, we would have an additional function approximator G, and these would actually be our control Lyapunov functions. And we'll have a GP estimators. So we are essentially doing Gaussian process regression online. And what that models is the evolution of the difference of G in successive time steps. Okay. So essentially what that means is G is a function approximator that approximates the constraint return of cos C, and then we are treating the difference of the G's in successive time steps as noisy observations of the Gaussian process of G. Yeah.
Can you define trajectory-based safety more precisely?
Yeah. So if you look back to this particular formula, right? Then you're essentially saying that the constraint return. So this we are doing. So this is going from t to infinity, right? So this gamma is the discount factor. Right, this is the cost function, and sometimes it does not have to depend on xt plus 1, right? So we want the expectations of these to be less than some.
What do you mean by trajectory-based safety?
Yeah, so
that property should hold the expectation.
The
expected value should be
less than some known threshold, and that's sort of in this particular constraint policy optimization formulation. But in general, the difference as opposed to state-based safety is that you don't just check whether the cost at a particular state for performing a specific action violates some threshold. You're looking at long-term cumulative cost. Okay. Yeah. Does it make sense?
When you say you want to approximate a real value function, etc., you are approximating that.
So, yes, we are approximating this. Yeah. Yeah.
I see. And then so go back to the, yeah. And what's the control function?
Yeah, we have more slides. So, but in this case, essentially what you recognize, at least D would act as a control Lyapunov function, at least in the discrete time setting sense. So the observation here is that these function approximators, which we call the guard network, is actually would be a valid control Lyapunov function for discrete time control Lyapunov functions if it satisfies these, right? So essentially, this would be like the derivative of G, and if that's greater than 0, then it would be, and also there's of course some condition on the G itself, then this would be a valid control Lyapunov function. And so the observation here is that we are trying to, so this particular difference we are treating as noisy observations for the GP model. So with GP, you have this particular probabilistic guarantee. So with 1 minus delta, the ground truth G that models essentially the evolution of the safety would be greater than some lower bound L. Okay, so we can get L. And of course, this improves as you get more samples with exploration of the learning agents. Yeah.
If the control Lyapunov function doesn't exist, what does your analysis end up converging to, or does it?
Yeah, so we are kind of enforcing this, right, so that it will be. What if one doesn't exist for these?
Will you end up finding one that's erroneous?
Yeah. So that's a great question. So I actually, you will connect to this point. So essentially, I have a new constraint optimization problem that essentially says I want to find the optimal policy such that the lower bound, right, for this GP estimates has to be greater than 0. So first of all, this is some statistical guarantee. So we are just borrowing the notion of control the Lyapunov function here to enforce this particular constraint. And the second thing is this cannot be enforced analytically, cannot be enforced directly because I have to do a GP estimate for this. So I don't have an analytical form of LSA. So what we end up doing is we can only enforce this softly. So which means that we can, in reality, to solve this constraint optimization, I may actually violate this particular condition, and which means that G would not be an actual control Lyapunov function.
If you end up converging, can you detect if it's wrong?
We can check whether that constraint is satisfied, right? But what type of guarantee do we get? Is at least if we can enforce this constraint during our policy search, and based on the statistical guarantee that we get with GP estimations under some assumption on the RKH norm of the function, then we get the safety of the policy search, right? So it's guaranteed to go in a way that reduces the cumulative safety cost.
If CLF exists, will it find it?
I don't think it's a complete solution, right? So we don't have any completeness guarantee. Yeah, I mean, G is just a function approximator. Yeah. All right. So so there's some practical considerations. One is that we have to do this online, right? So I've already mentioned that we don't have an analytical form for these, so that constraint optimization cannot be solved directly, so we can only enforce this softly. For example, you can use a big M trick. There's also the issue with initialization. So for high-dimensional task, if you just do this, then you might end up with a model that actually converges quickly to an incorrect estimation, and then it gets stuck there. So we assume that for a high-dimensional task, somebody can provide some small amount of information about how a safe trajectory look like. So in our experiments, we just use a single safe trajectory to initialize the GP for high-dimensional task. For low-dimensional systems, you don't actually need to do that. The other important aspect is that we are introducing an additional component in learning, right? So we have to cope with the overhead of doing the Gaussian process estimation. So one thing that we can do is we can fix the dataset size because the complexity of the GP estimation is cubic in the number of data points. So you have to manage that. The problem with fixing the dataset is that now I have to decide what new data to incorporate and what old data to delete. Okay, for instance, I have to eliminate highly correlated data, and I can use this particular test to identify data points that I can delete. Okay, so this is a bunch of tricks that we do to cope with the overhead of GP estimation. So let me show you some results. We have video demo as well. So we look at this particular environment, which is called half cheetah. You can see that only has 2 legs. It actually has 17 continuous state components, and we don't know the dynamics of this system. Okay, this is a fairly busy slide. We tried 2 different safety cost functions, so 2 auxiliary cost function designs. One is related to the rotation of the torso of the cheetah. The other is related to the height of the body relative to the neutral position. And we want to avoid this type of catastrophes, which means that we want to avoid falling down, okay, and also not being able to get back up. So if you compare the average episode reward over training iterations, then The orange and the yellow lines represent the approaches that uses GP estimation to guide the policy search. And you'll notice that we actually have a side effect of accelerating learning for this particular case. So the average episode reward actually increased fairly rapidly compared to the to DDPG, which is one of the state-of-the-art techniques for doing model-free DRL. And so the green lines are somewhere here at the bottom. Okay. And I call this a side effect because in this particular case, the goal is for the cheetah to move as quickly as it can, which means that performance, so safe behaviors is related to helping it to perform. But in other scenarios, you might have a situation where staying safe is actually at odds with being more performant. Okay. So if you look at the cumulative catastrophes, our approach essentially would stay close to 0. If you apply DDPG, again, which is the state-of-the-art algorithm for doing model-free deep reinforcement learning, then it just increases linearly as the iteration goes on. We also compare based on wall time instead of iterations because we want to see whether this GP estimation introduces a lot of overhead. And it turns out that we also outperform DDPG when we compare based on wall time. So the average episode rewards increase a lot more rapidly than DDPG. And also, you can see these bottom 2 dashed lines, which are the cumulative catastrophes, okay, which just stay at the bottom. Okay.
Question?
Yeah.
So then you have this guard network.
Yes.
Whenever you enter an unsafe state or something, like get close to it, like you apply that controller, or like?
So the guard network essentially would act as a control the output-off function. And what it produces is a constraint on the policy search. So you have this constraint optimization problem where you want the lower bound of the GP estimate to be greater than 0 so that the guard level actually would function as a control the output-off function. So that in the long run, I would be reducing the cumulative safety cost. And eventually you should get to 0. Yeah. So we are doing this concurrently as we are doing the approximation of the value function. Okay, so let me just show you a video. So again, here the performance goal is to move as quickly as we can and have 2 cost functions. One, the cost function is related to the magnitude of the rotation of the torso. So this is iteration 1. So this is DDPG. So already iteration 5, our approach can achieve a relatively high returns, whereas DDPG will still fluctuate and you can get to some interesting type of behaviors like moving with the head. Okay. And this particular is, again, safe behaviors correlate with behaviors that has good performance. Okay. So we can actually learn very quickly, and also you can see that in this particular case, the cheetah stays safe, right? It doesn't fall down, right? That's our safety goal. And return just means that it runs quickly. You can really see it in this video. So the point about these 2 different cost functions is to show that our approach is quite flexible with the cost function design, because if you think about reinforcement learning in general, it depends on the design of the reward function. So naturally, you can ask, do we have the same issue with cost function design? So the point here is to show that, while this cost function has some correlation with whether the cheetah will fall down and unable to get up, we don't need a whole lot to get good and safe behaviors. Okay. So again, you would have fluctuations with reinforcement learning in general, but quickly after 20 iterations, or actually after 50 iterations and so on, you can already achieve a very high returns, whereas DDPG would achieve the same returns, I think, after a few million iterations. Okay. So there's order of magnitude improvement in terms of acceleration of learning But I want to again emphasize that that's a artifact of this particular example, because again, being safe helps with performance. Okay, so I think I'm out of time. So just to conclude, so we look at the reachability problem of neural network control systems. And the idea here is to couple Bernstein polynomial regression for the neural networks with a adaptive sample-based error analysis. And the key is that we can, in fact, control the Lipschitz constant of the neural network controllers during training to get some additional mileage for the reachability analysis. And we're interested in the problem of, hopefully, improving the safety of model-free learning. And in that case, because you actually don't have the dynamical model of the system, then we don't have a formal proof. So the question is, how do we improve safety for these type of systems? And again, these systems might actually have to interact with the real environment during training, so you cannot have these systems crash a lot in order to learn. So the final concluding remark is, while we've some success in verifying this system, there's still a very big gap between the type of systems that these verification tools can handle, and the type of the systems that people have demonstrated some interesting success or interesting behaviors for neural network control systems. So, hopefully more people would work in this area to bridge this gap, and we have some ideas also how to bridge this gap as well. And happy to talk about them after the talks. So, any questions? Yeah. Thank you. Yeah.
Trying to understand the scalability issues for the first.
Yes. So.
You said it's hard to scale for more than 6 or so dimensions.
So the dimensions.
How much of that is due to the neural network, and how much of that is due to the plant model? Because you're.
Yeah.
If you had a non-neural network controller.
Right. Sure.
Strategy.
Sure.
Right.
But imagine maybe your plant model is very simple.
So I'm trying to understand
right.
that. In your experiments, what was the plant model?
So these are nonlinear continuous systems.
Okay.
You can go to. I don't think those examples include any hybrid systems. We can. So there are inherent sort of limitations if you look at nonlinear continuous. And then maybe continuous system with nonlinear dynamics or even hybrid systems. So those, of course, you cannot handle.
Have you tried substituting out the neural network or something else, a really simple controller?
Yeah. So the question.
Reachability
Yeah.
and seeing how you still have scalability issues, and the problem is elsewhere.
Yeah. Yeah. So I think there's actually two points with that question. One is if we replace the neural network controller with something else and see whether we can still answer the reachability questions. The other is why if we take one more step back, is why do we actually want to have neural network controllers in the first place? So maybe something else already works. So let me answer those in the reverse direction. Is that there's a lot of techniques these days to train neural networks, right? So training is relatively well developed. There are many strategies involve reinforcement learning and so on. And so I think we are at the stage where you can get fairly good performance with neural network controllers. So now the question is whether they're safe when you actually use them for reachable properties. So the second question is to replace these and understand where the computational complexity comes in. So I can say is that for just with FlowStar, so it's a bit of a hard question to answer. So if you have a very bad controller, then quickly it would explode, right? So the reachable set would also explode very quickly because the controller is bad. It's not able to, for example, stabilize the system or get the system close to some reference trajectory. So that's one challenge of doing that exercise. So the controller has to be good, right, in some sense to analyze that. So then you can actually look at, for instance, just a simple polynomial, right, that maps from states to controls. So in our analysis, we actually look at where the kind of why the error term blows up when we do these Taylor model constructions. And we don't have a consistent observation. So for some examples, so the answer is this. So the answer is that we have a set. So it blows up because only for part of the state space, it blows up the error term, and not for the other parts. So I don't know, it's a long-winded answer to that question. But in some sense, we are using the same ideas to approximate a sort of maybe a complicated neural network with a simpler input to output mapping for verification. Yeah. Okay. Yeah, sure.
You thought about using the two objective gradient descent algorithm you mentioned to try to maybe train networks that were resilient to adversarial examples. It seems like it's quite closely related, right? I mean,
To adversarial.
Examples means you have a very large Lipschitz constant, right? That is for continuous networks. And one could imagine trying to do something like that where you switch off the actual loss function you're interested in and something to try to reduce the Lipschitz constant. I mean, it's related to
It's related to, yeah, it's related. So the reachability question of just neural networks is related to adversarial robustness. And that's why people are also interested in computing a tighter bound on the Lipschitz constant of the neural network. In it itself is I think it's a research question. So we haven't, the short answer is we haven't tried that. And I think, and
the point is that your technique could be useful for robust adversarial training.
Yeah, potentially. Maybe the challenge is that we would then be looking at global robustness, because this is a global Lipschitz constant. Whereas for adversarial training, you're actually looking at local robustness.
but
Yeah.
global robustness would actually be good.
Would actually be good. Yeah.
It could be that it's impossible to get a network that has a globally small Lipschitz constant and still fits your actual problem well.
Right.
But it could be
Right.
interesting if there are some problems for which that's the case.
Yes, absolutely. So I think that's a very nice suggestion. So I think for some application, it would be good to actually yeah. So it would be good to have a certification on global robustness. It also depends on where your decision boundaries are. So if you have the data point very close to decision boundaries, then your epsilon is going to be small, right? Your perturbation is going to be small. And maybe for global robustness, the right way to approach the problem is actually to look at statistics, or maybe a probabilistic certification, right,
Yeah,
instead of
even
these.
for things where you are close to the decision boundary, if you look at the Lipschitz constant before the softmax.
Yes.
Right? I mean, ideally, even near the decision boundary, those final values before you make a selection should be.
Yes. Yeah. So So you're right. So in fact, I mean the reason that people are interested in getting a tighter bound for the Lipschitz constant, at least part of a lot of people are looking at this robustness, adversarial robustness. I mean, there's some recent work where they make the argument that it's related to control. There's some work coming from UPenn, and again, that kind of motivates. They just want to say that we want to get a tight estimate of the Lipschitz constant. This is from George Papa's group. Just to sort of motivate that analysis from the controlled angle. Yeah. Sure.
In your half cheetah example,
Yeah.
the safety cost is your violation of the angle of the.
Yeah. So let me maybe explain. So we play with two safety cost function. There's no threshold. So again, I want to contrast our approach with constraint policy optimization, because in CPO, you need to know the threshold. Whereas here, there's no threshold. I mean, I don't know, right? Whether a large body rotation means that the cheetah will fall, because there are other parts of the system, right? So that maybe the legs can keep it standing, right? So it's really a specific configurations that the cheetah will fall and then and not even able to get up. So these are just auxiliary cost functions that correlate with this type of failures.
So is the intuition basically you penalize when it's harder to recover back to the safe trajectory?
Yeah, so large body rotations would probably correspond to this type of catastrophes. The second is the body height relative to the neutral standing position. If that value is large, then likely that the cheetah has fallen down. So these are just some proxies to estimate the safety. But so the point here is that even with those somewhat approximate safety cost functions, we are able to achieve safe behaviors. So you can actually see that the cumulative catastrophe actually stays at 0 for the cost function that uses the body rotation, essentially the magnitude of the body rotation. Yeah. Does it make sense? Yeah. I mean, again, the performance goal is for this to move as quickly as it can. So if it doesn't fall down, of course, it would move fast, right? So that's why we get this acceleration in learning. So it's just, again, an artifact of this example. Yeah.
I guess my biggest confusion was how you read that off of the Q function, which is...
So the other parts would just proceed as normal. So this would proceed as normal. The additional part is this guard network, all right? And this would act as a control Lyapunov function. And we treat the difference in the output of G in successive time steps as noisy observations for the Gaussian process, little g. So then the optimization problem, right, this is what you would do, right, but subject to this particular constraint on the lower bound of the Gaussian process estimation. The problem is that we don't have an analytical form of these, so you cannot solve this problem directly, or you cannot enforce these, because otherwise I would know that, to answer maybe your question earlier, then I would know that I cannot satisfy this particular constraint, right? Then I would know that at least for this particular neural network approximator that I chose, I was not able to find a control Lyapunov function. Yeah. Okay. Okay, so I'm happy to take questions offline as well. Yeah. So thank you again.